All right, let's do 6.56 from the end of the chapter. This question basically asks us about 1 mole of water vapor or steam condensing to liquid water. So we're going from gas phase water to liquid water. We want to know, is delta H negative or positive for this process? Now, I'm going to answer more than just this question for you, okay? What I'm going to do is I'm going to consider lots of phase changes and what happens when materials change physical state from liquids to solids, gases, so on and so forth. So I'm going to build a data plot, all right, and talk our way through this as we go. It's important to know which phase changes are endothermic and which phase changes are exothermic. And this answer to 6.56 is going to help us with that. And that's why I chose to highlight this problem in a video. So let's start with a solid. Maybe it's water, an ice. It can be really any solid, okay? And we're going to start and hold that sample of material at a temperature well below its melting point. So it's going to be a solid. What we're going to do is we're going to start to heat up that sample. And what I'm going to do here is make a plot of the temperature of the sample versus the quantity of the heat added. This would be measured in joules. This would basically be our Q term, okay? How much heat is being added to the sample. So I start with a solid, just a chunk of solid, maybe it's ice. And I start adding heat to that solid. What does this plot look like? Well, while the material is a solid, as I add heat to it, the temperature of that sample will start to heat up, just like if I had a block of aluminum, okay? And I start adding heat to it. The aluminum heats up in accordance with what? Its specific heat. How many joules per gram is required to raise a temperature, 1 degree. And the slope of this line would be, useful to help figure that out, perhaps, okay? So the material is still a solid. Now, an interesting thing happens when I get to about this point. Now, how am I going to define this point? Well, this point, I'm going to say, is the melting point of my solid. That temperature corresponds to the melting point. And it turns out that what happens there is this plot levels off as the material melts into a liquid. And what are the consequences of that leveling off at the melting point? Okay? Basically what that means is that I can add more heat energy to my sample, but my temperature does not rise. Line flattens out. So what happens to that heat? It turns out that phase changes might require an energy input to occur. Depends on what direction you're going. More on that here in a little bit, okay? In this particular case, the conversion of the solid into the liquid form, which is going to exist over here, requires an input of energy. It's an endothermic process. So this quantity of heat which we add is only used to convert the solid into a liquid. There's no temperature change. It just converts the solid to a liquid. It melts into a liquid. Okay? That heat is known as the heat of fusion. Now, fusion, you usually think of like nuclear reactions or something, but this is just melting, okay, into a liquid. It's just called the heat of fusion. Now, after all of the material melts in a sample, what's going to happen is we're going to start to get an additional increase in temperature. I'll just draw that line like that, okay? This section of our plot corresponds to warming up the liquid. So we've melted it, and now we're going to warm up the resultant liquid. It's going to have a different slope than this one over here, and that's why I purposely kind of exaggerated the slope there, okay? But we keep adding heat. After we've melted it all, the liquid will start to warm up. So the temperature will rise as we add more and more heat energy, okay? But then another interesting thing happens. At some point, this plot levels off again. And it turns out that this leveling and that occurs for quite some time, or quite some heat energy added instead of time. Okay. That point is our boiling temperature. I'll call it here my boiling point. If I'm working at 1 atmosphere, that would be the case. Okay, I'm at a standard boiling point. So we heat up the liquid until it boils, basically. And as it turns out, we can add more and more heat energy to our sample, and the temperature doesn't change, it just stays at the boiling point. Okay? Of course, what happens there is this process of vaporization, if I'm moving towards the right. I might call that the heat of vaporization or the enthalpy of vaporization. And what that is this quantity of heat that's required simply to vaporize my molecules from the liquid into a gas. Okay? And then after I make the gas, and I convert all my molecules to gas, the temperature can keep increasing. If I add more and more heat, I can make the gas hotter and hotter and hotter and raise its temperature. But the key idea is I'm stuck here at the boiling point temperature. Even though I'm adding more and more heat energy, I'm stuck here at the boiling temperature until all of my liquid is converted into gas. And once that happens, I can heat up the gas more, but I got to convert all of my liquid into a gas first. I got to evaporate my liquid, if you want to think about it that way, okay, in terms of what we're familiar with water. That requires a tremendous amount of energy input, as it turns out. If you're going from the liquid to the gas, a tremendous amount of energy has to be added. So the gas phase is up here, and here in through here, this is our liquid, where our liquid exists. And that would be between about here and here, where we melted it all, okay? So solid, liquid, and then gas over here. We really got a liquid in through here as well. We're just vaporizing it, so I guess I should include that. This is all liquid, and in fact, in through here, the liquid would be boiling, okay? But it requires a tremendous amount of energy to vaporize our liquid into a gas. The reason why that is because you have to break apart all the molecules and their intermolecular forces. And you probably don't know a lot about, when I say break apart the molecules, I don't mean degrade them. So for instance, you'll have liquid water before, you'll have gas phase water after this phase transition, okay? But you need to separate the molecules from one another. And it turns out that water molecules are attracted to one another through these so-called intermolecular forces, which we don't know a lot about right now, but they're reasonably strong in the case of water. And because of that, we have to have a tremendous amount of energy input to separate those molecules, to make them into a gas, okay? So back to the original question then. It tells us about this, it asks us about 1 mole of water vapor, and we're condensing, okay? So we're actually going from the gas to the liquid, okay? We're going the opposite direction. The way we describe this is that an exothermic process or an endothermic process. And it turns out that the condensation, that's what this is talking about, is an exothermic process. All right? And vaporization or evaporation, which is the reverse of condensation, is an endothermic process. So to evaporate or vaporize, to make into a gas, requires an energy input. But condensation, going from a gas to a liquid, is an exothermic process. And because of this, burns caused by steam can be really, really devastating to skin, okay? And the reason why that is because not only is steam really hot, and you got to cool it down to liquid water, temperature of your skin. So that just the cooling process requires, some energy to be transferred to your skin. But to get from the gas phase to a liquid, you get this huge amount of energy back that's stored in this so-called heat of vaporization. Okay. So when it condenses to a liquid from steam, get a lot of energy back that's transferred to the skin can cause really bad burns, okay? So condensation is an exothermic process, negative sign, okay? Now, what about phase transitions down here involving the solid? Okay, so melting. Okay, and then we have the converse to freezing. Are these endothermic or exothermic? Well, let's think about it. Going from the solid to the liquid requires we input this energy. Okay, so melting, endothermic, freezing, exothermic. Okay, so hopefully this discussion has familiarized you with which of these processes are exothermic, which are endothermic, so that you can understand that and successfully predict if you're faced with such a problem.